let's get this closing keynote on the way. As Jens said, I had to choose a topic, and I've not chosen a topic, probably the topic that is most dear to me. So I entitled this talk, Breaking Dependencies, the Path to High-Quality Software. So now I skipped the introduction, this is what Jens has done, and I immediately jump to the question that you might now have. What is high-quality software? So, many of you might now believe that it's another talk about C++20, C++23, but that's not the kind of talk I'm doing. I'm usually doing the talks about other topics. So for me, my definition, you might disagree, but still, high-quality software is easy to change, easy to extend, and easy to test. So now, for the entire talk, this will be my definition of high quality. It's about, changing things easily. And I actually believe this is truly, and of course, fast is important too, but for now, for this talk, let's focus on the three red items. And this is just so much the truth in our industry. Software must be adaptable to frequent change. This is it. And it's actually in the name already. Software. So the soft actually comes from the fact that people expect that it can be changed easily. It is just from the very beginning, it was from the very beginning the thing that needs to change. But if this would be always true, then it would be simple, right? It's not always true. And from your own experience, you know that things are not easy to change very often because there is a very basic, a core problem in all of software. And this core problem that keeps us from adapting easily is dependencies. Now, I spent years to actually collect quotes from famous people about dependencies, and there's quite a few, but I still kind of favor the one from Kent Beck, the inventor of test-driven development, who said, dependency is the key problem in software development at all scales. And this is such a simple formulation, but so true. Whatever you do, it's always about these dependencies. It's always about dealing with the little connections, the relationships between classes, modules, little things and big things. And so this is what I've done over the years. I've talked about dependencies. I've talked about the solid principles, type erasure, design patterns as such, the visitor pattern and type erasure again. I've talked a lot about this. And so from these titles, maybe a little subtle, but you might get the idea that all of these talks are about breaking dependencies, dealing with dependencies in one or the other way. And so, well, to say it in other words, the common theme for me is software design. So I don't talk about features, I don't talk about the standards, I talk about the other thing. I try to talk about the topic that nobody else wants to talk about for some reasons. So, when I see software design, I should actually define software design real quick. Because this is the first thing that we now might have different ideas. Wikipedia itself actually doesn't define software design with just a few words. There's no clear definition. There's at least two at Wikipedia. And so here's my definition, which you might agree with, might not, but this is now exactly what I will focus on. So software design is the art of managing interdependencies between software components. It aims at minimizing, mostly technical dependencies, and introduces the necessary abstractions and compromises. So this is a little long, I know, so I try to shorten it. Software design is the art of managing dependencies and abstractions. And so I really think this is not something that is easy to define because it is an art. It's not something that you just do. It needs the experience, definitely. And this is why it is kind of hard. But it definitely is always about managing dependencies, dealing with them in one way or the other. Hopefully minimizing them, of course, but at least reducing them in order to make our software a little more flexible, easier to change, extend, and test. But it's also about dealing with any kind of abstraction that helps us to deal with the complexity. So, Yeah, thinking, okay, what's the big deal? Why is this something that we should talk about? It's so obvious, isn't it? Well, okay, allow me to tell you a little fictional story, which might involve you, but you can choose whether you're part of the story or not. Let's assume that there is a new project. So you might be on a project or not. And something that is very rare, you can actually start fresh. You can start on a totally new project, which already sounds pretty amazing, right? Oh yes, it does. And so initially, for the first couple of months, life is heaven. It actually is. You can do whatever you want. You can write whatever you want. It just works. It's fascinating. There's no problems at all. And so, of course, as a consequence, managers feel like you will rule the world in just a few other months. And they start promise to any customer that this feature and this difficult thing will be available in just the next release. But it works. Everything works. Everything's great. And of course, after some time, after a few months, the speed of development kind of starts to decline. Because nobody really thought about the quality of the code. Everything was just done rather quickly, simply because it worked. But eventually, things are starting to get a little more difficult to change. It gets more difficult to add new things to the code, because nobody really thought about the future. It was all about the present. And while in the beginning, everybody was like, "Ooh, I have a little time left. Let's do this extra thing." Now there's less time left to do this. There's less time to go this extra mile, do this extra work, according to this Boy Scout rule. So, of course, there's less time, right? There's less time now to actually deal with the real problem. And so it's kind of hard to get back to the initial quality. So what now happens over time is, well, of course, that quality degrades even further, which puts everybody in a pretty bad situation, because now people have even less time, because suddenly there's more bugs which need to be fixed, and this takes a lot of time. And it takes even more time to actually change things and add new things. Deadlines are now at stake. You're not as quick anymore as before, but you've already promised all this stuff. Oh my, this is a very, very bad situation to be in. And so, what for sure happens in this situation? Of course, new people are hired. Just increase the size of the team, make everything twice as fast, which of course results in another decrease in speed. Obviously, because now the old people have to train the new people. They have less time to actually deal with the code. It's going downhill. And at some point, you reach actually your speed might go up eventually a little bit again, but eventually you reach a point of maximum frustration. This is the point when many people decide it's not worth it anymore. Key developers start to leave the project. Life is definitely not great anymore. Now you're totally depressed, I know. It was a bad thing to tell a story, but I also said it's a fictional story. You could decide whether you're in this or not. But I'm afraid that, many of you feel like, oh, I know this. And I actually have to admit, it's not so fictional at all. I'm a freelancing trainer. I'm not in any of these projects, but I actually tried to help some of these projects, and I've seen them degrade even further. It's kind of hard once you get there. So, to the bottom. And so, quality matters. Quality does matter. Of course, it matters so much how you implement the code, the implementation details. It matters that you take care of duplication in code. It matters that you make code readable. It matters that you take care of the little details. But although this matters, the structure and the organization of the code, in other words, the design, matters so much more. Because this is essentially what results in good or bad projects. And so, again, my personal opinion, the design plays a much more central role in the success of a project than any feature could do. Good software is not primarily about the proper use of any feature. Rather, it's about solid architecture and design. Good software design can tolerate some bad implementation decisions, but bad software design cannot be saved by the heroic use of features or old or new alone. And so, software design, software quality does matter. Now, unfortunately, it's not just my observation that this is exactly what usually is not taken care of. So I now quote Robert Nystrom, the author of Game Programming Patterns, who apparently has made exactly the same experience. I have to say that he is from the gaming industry. Games are very time critical, so it's kind of a usual thing, but it's not just in games. But the architecture this code hung from was often an afterthought. They were so focused on features that organization went overlooked. And indeed, I believe this is exactly the problem that you find in a lot of code bases. So, now you may be in a code base that just does not work well anymore. So you have ignored software structure, organization. You did not really spend a lot of time on thinking about design. But you know what? There is good news, because of course you can always rewrite the code. Of course. Sounds great, right? But there's a catch. There's a catch that many of you may have heard about. So you might know this gentleman here, Joel Spolsky, who's actually the co-founder of Stack Overflow, and also, I think not so much recently, but has written a pretty successful blog, so Joel and Software. And there's a great article on exactly this particular issue, rewriting the code base. And this is, I believe, the key sentence from this article. They, this here actually means Netscape, made the single worst strategic mistake that any software company can make. They decided to rewrite the code from scratch. Does anybody remember Netscape, the browser? Okay, this is the slightly older people. It's not here anymore. Why? Well, they tried to rewrite the code, it utterly failed. So apparently, you cannot just fix everything overnight. It doesn't work. And so software design matters from the very beginning, and it is a continuous effort. It is work. Now, I'll try to give you another example. An example that now some of you will not understand. You might not be old enough yet, but I promise you, you will eventually understand, and perhaps you have an intuitive understanding for it already. So, do you know what this is? So, it is a messy child's room. By definition, this is now what the younger people don't know. By definition, a child room is messy if you go from with a blindfold, go from the door to the window and you step on something. That's a messy child room. Now, if you're a parent, what, of course, do you ask your child to do? Clean up, tidy the room. What's the result of your, of course, nice request? So, the result is a pretty angry child who's absolutely not interested in cleaning up the room. So now, of course, initially, I'm also just a young parent, I thought they're just lazy kids. But later I found out that there's a totally different problem. They have just no idea where to get started. For them, this this unclean mess is an insurmountable problem. They just don't know where to get started, and this is why it's such a big pain for them. And this is exactly pretty much what software is about. So, keep your room clean all the time. There's no problem. You know exactly how to clean up the little things. Everything works. So software design does matter from the very beginning, and it is, although it sounds like a lot of work, and it is a continuous effort. All right, so keep your code easy to change, easy to extend, and easy to test. This is now for you, the developers. This is what you should keep in mind. But now, of course, this requires extra work. And extra work means that some managers have to agree that there needs to be refactoring, etc. So what can you tell them to actually allow you to keep the code clean, to just not tighten the deadline such that this is impossible? Well, usually there's just one, and exactly one argument that they can give. It is about money. Seriously, it is all about money. Clean code, good code is cheap because you can actually walk forward quickly. You can change and extend things rather quickly. This is cheap. A mess is absolutely expensive. So whatever money you invest later to refactor things, it's so much more than to, from the very beginning, keep the code clean. However now, obviously you're asking, so how can we keep the software easy to change, extend, and test? So what do we have to do? Well, there is an easy answer. And of course, all of you know about this answer. The solution are design patterns. Design patterns. This raises nice memories, doesn't it? It raises memories, and it immediately raises an image of this book. Glorious times. The Gang of Four book. Gang of Four book because of the four authors, Gamma, Helm, Johnson, Felicitas, who in, actually it's hard to believe, 1994 collected design patterns. By the way, this is a seriously important thing to note. These four guys didn't invent patterns. You never invent a pattern. It's never invented. They kind of discovered and extracted these patterns. They took a look at the code bases at the time and actually tried to find common solutions to the recurring problems. And if a solution occurred in many code bases, apparently it was some kind of pattern. And so all they did was to actually give these patterns names that you can use to communicate some intent. When do I use this particular pattern? In which situation, for which kind of problem? And they, of course, in some way, show how this pattern helps you to manage dependencies. That's what they did. And despite the fact that this now sounds like they did not a lot of work, this is an absolutely amazing source. Still, despite the fact that some people regularly complain that it's so old. Okay, it's a little boring, I admit. It's very dry if you read it, but it is a fundamental source of the solutions to deal with software. So from my point of view, this is definitely still some very important thing because design patterns simply are everywhere. But we don't really talk enough about software design and design patterns. We don't really talk about them, despite the fact, and I'll try to point out, it's so important, so fundamental. We don't really talk about it. And just in numbers, and I know Jens will not like this, but still, in numbers, meeting C++ 2022, I now counted the number of talks in the live schedule, and so I might be off. So it's approximately 47. Perhaps it was one or more, one less, one more, not so important. Then the number of talks in C++ feature and standards was at approximately 16. By my account, might differ a little, but I think it was 16. The number of talks on, 34%. And the number of talks on software design, 4. 4 talks. So approximately 8%. And this is the reality that I'm seeing pretty much everywhere. So I have another number, which I cannot prove. This is not something that was official. So for CPPCon, we usually submit classes upfront, usually almost a year upfront. And had been 16 classes proposed. Exactly 1 class out of 16 was about software design and architecture. But 6 classes out of these, of course, we're talking about C++ 20 and 23. And that's the reality that I'm seeing pretty much everywhere. We talk primarily about standards, features, details, the implementation details. We do not talk about the big picture. We do not really talk about software design. So why is that? Why do we not talk about software design? Well, there may be a lot of reasons, but I've identified three. The three that I now want to talk about. 3 reasons why this apparently is not interesting anymore. Reason number 1, we already know everything about design patterns. What's there to talk about? Reason number 2, design patterns are just for object-oriented programming, and after all, object-oriented programming is not in favor anymore. And reason number 3, it's simple. Come on, it's just a couple of patterns. It is simple. Okay, let's take a look at these reasons, one by one, and let me try to make the point that I don't think that any of these is true. So, we already know everything about design patterns. And after all, they have been introduced 28 years ago. Now, almost 3 decades. Of course you know them, right? Well, now I have a lot to choose from, but I've now chosen one particular example that is bugging me quite a bit. I've now chosen the classic factory method design pattern, which is described in exactly this book. So let's take a look at the intent that the Gang of Four gives as a short summary, which is this one. Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to subclasses. That's a simple one, right? Pretty simple design pattern. It really is simple because, after all, it's about creating an interface for creating an object. What's special about this? Well, indeed, factory method is very often used pretty much as a synonym for creating something. And so, obviously, as a consequence, since C++11, people have more and more made the remark that Make Unique is a great example for such a factory method. It creates something. Now, let's take a look at how it is. Let's take another look at the definition, and let's take a look at what actually else is in there. Let subclasses decide. Defer instantiation. This, interestingly, is a couple of things that are usually totally overlooked that nobody really cares about, my feeling. And so, this is what the Gang of Four describes as the factory method design pattern. And of course, it's 1994. The one solution they usually have is to have an inheritance hierarchy. So there is some creator which has a factory method. This is where the name comes from, which is, you see, virtual. And some concrete creator can actually implement this method to create something. But again, there's some abstract product. Something that I don't really have defined yet, also some kind of interface. So this is how the Gang of Four describes it. Now, what they unfortunately did not do in the book is they did not draw a line. They did not draw a line right here in the middle. A line that actually shows something that is, I believe, fundamental to the idea. They did not show some architectural boundary. I believe this to be the core of what a factory method is. Up in the high level, I'll come back to the terms in a second. Up in the high level, we have all these abstract things, some product, some creator, and we can just use these without having to know anything about implementation details. We just don't care. But in the low level, we now are able to actually define what it truly means to create something. We can define the real products, we can define how and when they're created. So perhaps there is indeed something special. So we separate the use from the implementation details. Now, I have to go back to these two terms for second, high level and low level. I know this is two terms that are totally confusing, and there's usually always discussions when I talk about them. So, you now unfortunately have to accept these two terms as they are. So high level now in this talk means this is the stable stuff. This is the stuff that I want to depend on. This is the stuff that should not change, at least not often. Well, in low level, there's all the implementation details. This is all the little details that we eventually have to implement, but that you just don't want to know about in the high level. And so, as it is with this high level and low level, which by the way indeed comes from the fact that the abstract things are on the high level, so base class are on top, and the derived class is on the bottom, so low. Right now, as it is, this is an architecture. It is an architecture. So we could now talk an hour about what an architecture is, but to simplify it quite a bit, all the errors point from the low to the high level, all of them. So all dependencies run from the bottom to the top. This is what an architecture is about. Now, going back to, because of an inversion dependencies, this is kind of a key here. Now going back to make unique and so many other claims about little functions that just create something, this make unique function just does not allow me to customize anything. I'm not able to change how this works. I'm not able to change the little implementation details. So I do not mention any relationship in a make unique or in any little function that creates something. It does not invert dependencies or break any dependencies between entities. And so, yeah, I wouldn't consider that. And then there is one more thing. Actually, make unique is not a method. It's a function. And now, because I know this from my training classes, there is indeed not enough awareness. So allow me to give you a quick glance at the index of the C++ standard. And I'm using the current draft of the standard, so from November 11th. This is part of the index, of course, not the index. There is something that you do not see. Yes, you do not see method. There's no entry for method. There is no method in C++. There never was. It's a Java term that unfortunately was kind of ported to C++. Björn Stutzler himself actually made a comment about this in his the C++ programming language book. One sentence, very short. A virtual function is sometimes called a method. That's it. That's all about methods in the book. But though it's a short sentence, there is a key word in this sentence. Virtual. Now, with virtual, it actually indeed really refers just the term. But I'm not trying to go back to this factory method. Factory method. I don't think that any little function is an example for factory method. But it's something else. I know it's a little confusing. I think make unique is a great example for a factory function. Now, some of you feel like, oh my, this guy's just dealing with little terms. But there's a pretty important distinction. Because factory method from a word alone implies customization and function is not, we could now distinguish between these two. So, please from today on, use the term factory function for anything, use it as a synonym for it creates something. But please start to use the term factory method a little more consciously. Use it for anything that you want to be a customizable factory function. And immediately, there is value. Immediately, you can communicate. Here I have a factory function, and everybody knows, okay, just create something, great. But as soon as you now start to say factory method, whoa, you have actually given somebody else information. You consider this to be a customization point. You consider this to be something special. You can customize this in whatever way you want. that is definitely one of the primary ideas of design patterns. The names suggest some solution to a common problem. All right, so going back to my first reason, I think we don't know everything about design patterns. I don't think so. We might not even have the same terminology, which I personally consider to be a real problem. So I think we know a lot about design patterns already. But we definitely need to talk more about them. We definitely need to talk more about what do we mean when we say. Because these terms, they have so much information if you use them consistently. And so, I believe this is definitely one very good reason to start to talk more about them. All right, but this is just the first reason. Let's go to the second one. Design patterns are for object-oriented programming. But object-oriented programming is not in favor anymore. Now I know that you may have a different opinion. And I see this a lot, again, in training classes. And I'm perhaps talking a little bit about this inner circle of C++. And so you may have, as member of this inner circle, seen this talk, or at least heard about this talk, given in 2013, Inheritance is the base class of evil. Yeah, it's a funny talk from a title point of view. The title is brilliant, absolutely. And I think this is why the talk actually became pretty famous, although the same information was also in other talks. But this one perhaps is special because in the title it already carries information. You should not use inheritance. I don't think he really meant it this way, but he actually shows in his talk how we can live without better. And this is why this is really an important talk. But it carries a negative attitude towards inheritance. But there's actually people that can do even more. Perhaps you have heard this title or seen this talk even. Object-oriented programming is dead. Long live data-oriented design. Now, just to be clear that I'm not scaring anyone off, this is a CPPCon talk, right? CPPCon, every year there's 160 talks, give or take, and many of these talks run in parallel. 4, 5, 6 talks run in parallel. So what do you do in order to make your talk attractive? What do you do in order to make the people come to your talk? Of course, you choose some attractive title, some provocative title, and suddenly this is, of course, this talk was in one of the big rooms. No. Object-oriented programming is not dead. This is maybe perhaps true for the game industry to some extent. They were burned by object-oriented programming a little bit, and so this explains the title, and this is where this talk comes from. But it definitely is not dead. No. But this is now the attitude that some people seem to have. So in 2021, I actually had the honor to talk about design patterns in Jens's Meeting C++ online group. And so he put this online, and just within days, someone, I don't know whether gentleman or lady, I have no idea, someone posted a comment, really? Design patterns in 2021? Now, as I said, I have no idea who this was. And so I give it the reason of a doubt. Perhaps this person was trying to say something like, why do we talk about this? This is super common knowledge. I'm a little bit afraid that it's more the other direction. Why do we talk about this? Nobody needs this anymore. We don't do object-oriented programming anymore. So, this is one of these misconceptions that I definitely want to end, hopefully today. So, I claim, I'll show you, that design patterns are pretty much everywhere. You use them on a daily basis. And I kind of have realized now that this is exactly what people are missing because of the online voting that Jens showed us just before, where people voted for which patterns to use. Ridiculous answers, because I believe people have no idea what they actually do in this context. So I now go back to this book. I'll choose another one, a very famous pattern, very famous indeed, the pattern that all of you have to know. the so-called strategy design pattern. And so this is what the Gang of Four uses here. Define a family of algorithms, encapsulate each one, and make them interchangeable. Strategy lets the algorithm vary independently from clients that use it. So, how does strategy work? Real quick. You may have some context, some class that actually has to implement some kind of algorithm. Now, this algorithm is something that may be quite difficult to do, and so there may be a couple of dependencies. So you do not just want to have this dependency in the context. And really, this is the class where we now want to extract implementation detail from. We do not want context to be too big, too complex, and of course we also might want to have the flexibility to exchange implementations easily. And so the one thing that we now do is to extract this information. We isolate this concern into, and again, it's 1994, another base class, a strategy base class, which now represents the implementation details for this particular algorithm. Context does no longer implement the algorithm itself, but instead it now holds a pointer to a strategy. This is what the little diamond says. I now have a pointer to a strategy, base class, and so suddenly context doesn't really need to know about its algorithm anymore. It doesn't need to know about the implementation details anymore. And so I have now effectively separated concerns. I'm following the single responsibility principle. But this now enables me to actually add any implementation easily. I can implement a strategy, this algorithm in form A, in form B. I can do whatever I want to, which is now exactly what the so-called open-close principle tells us to do. We would like to design such that we can extend the kinds of algorithms easily. Now note, there's inheritance, yes, but still, the strength of this pattern is delegation. I now have a pointer to this space. It's not direct inheritance. This would fail utterly. This would not be a good idea. Again, though, they say an architectural boundary. I again separated the use from the implementation details. So, this is strategy, classic strategy, 1994 strategy. And this is what people see as the strategy design pattern. This is how you do it. But I think nothing could be farther from the truth. The standard library itself uses hundreds of strategies. But have you seen a strategy base class anywhere in a standard? Anyone? Not really, right? There's hardly any base class in the standard, so you can use one hand to count them. No, there's other strategies. So, unique pointer. All of you know unique pointer. What is often forgotten that a unique pointer has two template parameters. You usually see only one, so it's easy to forget, but actually there is two. There is T, the type that we want to deal with, but there's also the deleter, which is defaulted to default delete, which we use most often, but you can, from outside, tell the unique pointer how to actually deal with deletion. You can pretty much configure and customize this to your liking. You can inject this dependency. So, yes, this is a strategy. It's nothing but a strategy. It's exactly the same idea, exactly the same philosophy of give me the implementation, then I know what to do. And that's now gives you the idea that there's a lot. So, std vector also has two template parameters. It has a T and an allocator. So you can configure, you can customize a standard vector from outside to deal with any kind of allocation. That is a strategy. And of course, other containers might even have more. All of these for non-ordered sets, the hash, the key equal, the allocator, all of these are strategies. Compile time strategies. You may have heard another term for that. Andrea Alexandrescu actually introduced this term in 2001, policy-based design. That's the same idea, exactly the same idea. Now, one last example is to accumulate. Now we are in an algorithm. So we want to accumulate all the numbers in this vector of integers, 1, 2, 3, 4, 5, blah, and we'd like to sum them up easily. So we can use the accumulate for this task. So we pass the begin, the end of the vector. We pass an initial value of 0. It's a good start for a sum. And yes, as a fourth argument to accumulate, we pass the accumulation rule. How do we want to accumulate? Of course, you know that if we just want to sum up, we wouldn't have to, but this is again the point where we can customize the behavior. We can customize the behavior, and again, it's the same idea. It's a strategy. Of course, it's a little functional programming, so you also consider this a higher order function, but it's again the same idea. So there is hundreds of strategies all over the standard library. And that, of course, is definitely a sign that we're using a lot of these design patterns on a daily basis. So design patterns are everywhere. Indeed, we want to deal with dependencies. We want to deal with customizability pretty much everywhere. And so especially strategy, I believe, is pretty much everywhere. So design patterns are for OO? No. I think they're for so much more. So they're not only for OOP, but come in many different forms. So we definitely really should talk more about them. We should really talk about in which forms they appear, how they help us to make our software more flexible, keep it changeable, extendable, and testable. All right. There's one more reason why we actually do not talk so much about this. Might be. And this is that they're just simple. Come on, they're not particularly difficult. Well, let's take a look at an example. An example that I used a lot over the years, so if you've seen any of my talk, then it kind of is familiar. And I start to draw shapes. And a very common basic idea is that we abstract shapes in general by means of a base class. Of course, it's the most obvious thing to do. So it's a base class with, of course, a virtual public destructor. And now we have all the things that we need to implement in deriving classes. Draw, serialize, and maybe a few more little details that we need to deal with later. A few more virtual functions. Then there's a circle class, one of many possible shapes. The circle, first of all, of course, has circle-like things like radius, other data members, and there may be a couple of getters to actually use the circle properly, but eventually we'll have to deal with all these virtual functions. We need to implement draw, we need to implement serialize, and potentially a few more of these functions. Now, let this be just all the thing that we need. This is now what we want to properly implement. But as it is, unfortunately, it's a pretty naive approach. An approach that might work, of course, but that also might put us into a problem zone quite quickly. Because this naive implementation is actually causing a lot of dependencies of totally different nature. So the first kind of dependency is kind of obvious. It's the type of arguments. We are now depending on screens and byte streams and potentially many, many other classes, as we don't see all the virtual functions. This may be a problem, but it might also be okay. It entirely depends on what screens, byte streams, etc. are. However, how do we implement the draw function in Circle? How do you implement it here? Now, honestly, I wouldn't implement this myself. I would use a library for that. Of course, I would use any kind of graphics library, which, however, means that now our circle is coupled to this graphics library. This is kind of a difficult, kind of a hard dependency. Wherever the circle goes, we have to bring the graphics library along with us. So if the circle is used anywhere, the graphics library needs to be in the system, needs to be linked, needs to be part of the compilation. This is a kind of a big dependency. But it gets worse. We also have to deal with serialize. So how do we implement serialization? By means of a library, right? So I wouldn't do this myself. So suddenly we are also coupling to a serialization library, which we again have to drag along wherever we are using the circle. So this is going to be quite a heavyweight class, which, however, now also, and that's the last kind of dependency, couples totally orthogonal aspects together. Drawing and serialization. This is things that actually have nothing to do with each other, but still I have to deal with all of them. There is a lot of dependencies coming in. So there may be more. This should be sufficient to make the point. Now, how do you deal with this? And this is now where design patterns come in. So we have this naive solution. Now, what do we do? Well, we could, this is just internal implementation details, actually use a bridge. This might actually remove a lot of the physical dependencies. This might work if we have one implementation mostly. However, probably want more flexibility. So perhaps we should indeed use a strategy as shown before. But actually we need a strategy for drawing and a strategy for serialization. So should we better reach for a component design pattern? Or should we perhaps externalize all of these little details completely? Should we perhaps use external polymorphism? This might actually decouple even more strongly. But the style still would probably feel like 1994. Perhaps we need a type erasure implementation that very nicely combines a couple of these ideas to create a value type. This might actually be the right thing. But it might not be, because perhaps we actually want to have some kind of hierarchy of functionality, extendable functionality. Then we should probably reach for decorator. But now that I'm thinking about this, perhaps you've run in a completely direction at all. Perhaps it's actually not the implementation of the function that really matters, but the functions themselves. Perhaps this is what I should extract. Perhaps we need a visitor. And then, of course, there's also the slim possibility that I can resolve a lot at compile time. So perhaps I actually don't need these. I perhaps might need just something like a 0-to-p pattern. So I could now ask the rhetoric question, who knows all of these? But I save you the trouble. My point is, there's a lot of choices. There is many possible solutions. There is many design patterns to choose from. And of course, there is a lot of important questions to ask. So, well, which pattern should I use? What are the consequences of my choice? So, in other words, what are the advantages? What are the disadvantages if I choose that? And that ultimately is, of course, the important questions. Because every choice that you make will always give you some disadvantages that you will have to deal with later. There is no perfect solution. But there is an answer. Luckily, there is an answer that is quite commonly used. The answer is, it depends. It depends, which is actually the title of a CPP chat episode 80, that had the honor to be in I think it was 2020, okay, a while back. So together with Phil, John, Tony, and Tony, I actually talked about the solid principles. And this was fun. This was 1 hour of talking about structure and code organization. It was 1 hour where we actually could exchange ideas. And really, it was fun. But in the end, I asked the question, why don't we do this more often? This is valuable. This is actually good exchange of ideas and experiences. And both John and Tony actually answered, well, because it's actually difficult. It's actually so much more difficult to talk about this design stuff than it is to talk about features, than it is about talking about the new standard. This is easy in comparison, despite all the specific rules, etc. Design is tough. And so, no, design patterns are not simple. Definitely not. They are difficult. The single pattern might not be so difficult indeed, but in combination, this entire picture, this is really difficult. Software design in its entirety is difficult, very difficult. Probably the most difficult part of developing software that I'm aware of. This might be really the ultimate reason why we don't talk about this so often. There's just not an answer. There's not the answer. And so I do think we definitely need to talk more about these dependencies and software design. Absolutely. And now, having said all this, of course, there's people that talk about software design, of course. So here's a quick shout out to a few people that I really enjoy the talks. They are really about design. So Pete Muldoon, Charlie Bay, Tony Van Aert sometimes, not always, and also Mike Shaw. They currently talk a lot about, and always do talk about software design. But I definitely want to join this group. And so I actually spent 1.5 years to write a book on software design, which is, I believe, one of very few publications in this area. For that reason, it might indeed be something special. I really hope, because this is a topic that just does not get enough attention. Absolutely not. So it took me quite some time, and I believe that it's actually super important that you buy the book. Okay, not what you're thinking. Not what you're thinking. Definitely not. No. I actually checked out the competition. I checked out the bestsellers of C++ at Amazon DE, so now this is a German problem, I believe. And this is what I got, not yesterday, but a few weeks ago. So here, number 1, C++ Programmieren, Programmieren für absolute Anfänger, so a German book. And number 3, the XXL Wok cooking book. So number 4 is great too. Number 5, the XXL Diabetes cooking book. Come on, guys. Is this the books that you bought to up your C++ game? If yes, then actually here's your chance. You can actually change the list by investing in some real C++ book. Okay. Now let's talk about dependencies and software design, at least a little bit. And so let's talk about one of the most controversial patterns that we can possibly talk about. Let's talk about the singleton pattern. Singleton. I know exactly what you're thinking. How dare she? Has he no shame? Singleton in a keynote talk. But actually, I might not be so wrong. Just as Jen proved, this kind of seems to be the most popular pattern that we have. Most people actually know and use singletons. So let's talk a little bit about singletons and potentially all the way it's a problem. So first I go back to the Design Patterns book, which also, of course, defines the singleton, and this is exactly the intent. Ensure a class has only one instance and provide a global point of access to it. So it's one of the shortest intents. It's quite simple. And now there's a simple picture. A singleton is, say, a class that primarily has a static instance function. This is the one function that you can use to get the instance, the unique instance down here. So this is the one function that you need to call if you want to get the one instance. Everything else that would give you another singleton is just not able, you're not able to call it. So any constructors are private, copy constructors, any copy operation is prohibited, deleted or private, whatever. So you cannot really get access to anything that could give you another one. So instance is the one thing. Else, it's a pretty regular class. You have singled operations, whatever you need to do. You can get some data. You have access to member data. It's just special in the sense that there is one and exactly one instance. This, however, and this is please what you promise me now, this is not the implementation that we will use. Never, please. This is one of the reasons why the book is criticized. The code examples are just so outdated. Yeah, so this is definitely not what you should do. Please, you promise me? Okay. No, seriously, please do not use the code examples from the book. There is one common form of singleton that people usually consider as good. That is the so-called Myers singleton, which Scott Myers actually defined in his Effective C++ book. In the third edition, it's item 4. And it's definitely quite a clever implementation. There is the instance function, same name, which returns the reference to the database that we have. That database being my example. This is not a function that creates a static local object. This is the one database. When I enter the instance function for the very first time, this instance is created, since C++11, even in a thread-safe way, and returned directly afterwards. When I return to the function, so if I call it another time, I just get the same instance. Yeah, it's initialized exactly once, and so I will now always get the same instance again and again and again. Until, of course, at the very end of the program, this DB is actually destroyed again. Yes, so there is no resource leak of any kind because this DB object is registered via the add-exit function. It's destroyed at the very end, reliably. You don't have to do anything. Then, of course, as I said, there may be any operation on the database, so I can read and write, and please imagine there's a few more. But most importantly, I want to make sure that there's absolutely no way that I can get another database. So any kind of constructor is in particular the copy constructor and something like the default constructor are in the private section. Now, this little detail here, is interesting, which is now a little technical implementation detail. And now I'm differing from the design perspective. But if you actually default the default constructor in the private section, fascinatingly, you can create databases whenever you want to. Because until C++17, if you use an empty set of braces, you're using value initialization. And value initialization considers a database, at least potentially, as an aggregate type. And so aggregate initialization actually doesn't have to call the default constructor, but just creates the type as such, which is an interesting loophole. So until C++17, please indeed define the default constructor in order to truly avoid any kind of database instantiation. Since C++20, however, you definitely can default that. So let's use this database to for other. So let's keep this in mind for later details. Now, honestly, and this was the reaction you also had, most developers are not particularly fond of that. Why not? Well, again, to quote Robert Nystrom, anytime you make something accessible to every part of your program, you are asking for trouble. And that is definitely true for singletons because, well, we consider them anti-pattern because they represent global state. They do. And again, to quote some famous person, Michael Feathers, from his book, Working Effectively with Legacy Code, the singleton pattern is one of the mechanisms people use to make global variables. In general, global variables are a bad idea for a couple of reasons. And so just to give you a few that hopefully are kind of obvious. So global variables are generally a bad idea because they represent mutable state. And mutable state on a global level means that anyone can write and read whenever this person wants to. It's just so difficult to control, in particular in multi-thread environments. It's so difficult to deal with. So they're really hard to reason about generally. If you set be a singleton. And immediately after you call a get, you might not get the same value back. Very hard to reason about. And then in particular, they also are subject to the static initialization order fiasco, which means that there is potentially a binding order of things, initialization order. So the common advice is, don't use singletons. Which is indeed where the discussion usually stops. Don't use singletons. But I've seen that, well, most people actually use it. Why do so many people use singletons if actually we say as a community this is not a good idea? Well, to put it in the words of Guy Davidson, globals are bad, okay? And I actually talked to myself. I was not aware of these little connotations of the British language. Okay actually means like, we understand each other, right? So, yeah, sometimes perhaps, but generally not, right? So, yeah, we should avoid them, but there is some intrinsically global aspects in our programs. There always are, like the memory. Memory is always global. We have to deal with this somehow. Time may be a global resource, something that you definitely need to synchronize reliably. The system-wide configuration. In many projects, this is the one thing that people need everywhere in the code. Then, in computer games in particular, the audio, the display device. This is things that, well, should exist exactly once. The logger. And you may have a couple more ideas what is truly, from your perspective, intrinsically global. There are those aspects. But now, if we should not use singletons, then what should we do? Well, one thing is, of course, we could pass these things to functions. We could just have a lot of arguments, more arguments. But this is not really attractive, as also Robert Nystrom says. There are times when merely passing around an object is gratuitous or actively makes code harder to read. Some systems, like logging or memory management, shouldn't be part of a module's public API. And so, it seems that sometimes we just need singletons. Sometimes. This is indeed something I should stress, sometimes. But I believe there's an even bigger problem, something that people unfortunately do not see in that form. Singletons do create dependencies. Dependencies on concrete implementation details, things that happen in this singleton. And this is usually invisible dependencies. Somewhere in some function, somewhere in a code base, you now call the singleton. You might not be even aware of the fact that it's needed there. It's invisible. It's not part of the signature of a function. It's also artificial in many cases. It's definitely bad. It's a dependency that, let me show you. So, one slide in between. Singletons make it difficult to change, extend, and test because of these dependencies. So let's return to this database example. Let's return to this little code that we had. Abstract from this a little bit. Let's say that you just use this from some widget and some gadget. The widget is here, somewhere the code base. The gadget is down here. This may read, this may write. It's not super important. But they all definitely at some point have to use the database. They have to read and write information at some point. Cool. And of course, this is what you like to have. This is again what we would call an architecture. All the errors go from some low level to the high level. Cool. But once again, what did I say was high level? So high level is stable. This is the things that themselves have low dependencies. And the low level, I said, this is the things that are more volatile, malleable. That's where the high dependencies are. Okay, trick question. The standard library, Or let's just say the STL part of the standard library. Where in this picture is it? Is it up in the high level, or is it somewhere in a low? So it's on top. It's here. The STL is kind of the highest level we have. You have all the dependencies to the STL, but the STL has no dependencies on you, hopefully. So it's on the highest level that we have. And now from this picture, from this point of view, the database is now suddenly something like the STL part of the standard library, which basically means it never changes, which, however, is absolutely not true. The database, of course, represents an implementation detail. It's something that will change. The database is updated. We choose a different vendor. We rewrite the class. It's a big dependency. So this looks great, but actually this database is at the very bottom of the entire architecture. This is the reality. Everything depends on the database, which is itself a very specific implementation detail. And so this is not an architecture. And I believe this is why people tell you not to use singletons. They are architectural destroyers. Whatever you try to plan ahead in terms of architecture, you can very easily destroy this completely, fundamentally, by implementing singletons in this way. So, after all, again, singletons are pretty bad. We shouldn't use them, right? But then again, we sometimes need them for these intrinsically global aspects. So what do we do? Well, it might be very surprising to learn that there are a couple of singleton-like instances in the standard library. Seriously. And honestly, they work fantastically. So let me show you one example of how this actually is solved in the standard library. So this is now an example that I didn't invent. This is from CPP reference, somewhere in the realm of memory, polymorphic memory resources, PMR. So I start with an array of 1,000 bytes, which is totally enough for this little example. Yeah, it's not a lot of memory, but still. And this array is totally uninitialized. But this is now supposed to be the place where that I use for allocating memory. For instance, for the reason because I must not use dynamic memory. So I want to use static memory only. So now I use one of these PMR classes, a monotonic buffer resource. I pass all the information of this little byte array to the monotonic buffer resource. So the pointer to the first byte, the data, the number of bytes, the size, and therefore make this raw array ready to be a source for memory. And so I now pass this, my pointer, to a PMR vector, which, by the way, is not another implementation of vector. It's the same class, but the allocator is dealt with differently. So a vector of PMR strings. And now what I can do is I can very, very easily just add strings and then print them. And fascinatingly, all memory acquisitions in the entire program go into this little array. There is not a single new call, and still it works quite smoothly. Nice, nice, indeed. And in fact, for me, this PMR namespace is an El Dorado of design patterns. It's really fascinating. But now, for our purposes, there's just one little thing that I want to draw attention to, this little function call here. We actually need to configure how a monitor buffer resource, what it does when it runs out of memory. This might eventually happen. By default, it would just call new, get some new memory, but this is, of course, not what we want to do, so we now configure it with a null memory resource. Null memory resource being another allocator, which, however, never allocates. It always fails, it always throws an exception. Now, hence the name, null memory resource. But now this null memory resource is special. Because what you get, if you call this function, is the null memory resource. There's one. So this thing now indeed acts as some kind of singleton. Let's take a look at the definition again. The intent: ensure a class has only one instance and provide a global point of access to it. Now, we have a point of access. We have the function, null memory resource. And as the documentation says down here, the same value is returned every time this function is called, every single time. Is there only one? Well, try to create a copy of that, because all you get is a pointer to some base class. You don't even know the type of that fella. You have no idea what it is. You don't know the name, you don't know the type, you don't know anything. So how could you create a copy? So this actually does kind of the same thing as we expect from a singleton, but it's different, of course. Cool. Nice. But there's one last thing. Right now in this piece of code, we still depend on this particular, say, singleton, this particular allocator. Now, if this would be some other function that we want to deal with elsewhere, then of course we would like to gain a little flexibility. We'd like to customize which allocator is used at this point, not this specific one. And so what we might want to do is we might call get default resource, which is the function that gives you the global memory allocator set for the system, the system-wide default allocator. And get default resource might actually give you the idea that is also a set default resource, which we can use to actually define, customize the default allocator for the system. Oh, so at some point we can set this up front, and so the other code does not have to use a specific form, but it just uses what has been defined up front. Very nice for testing indeed. But now, when I think about this, indeed, this gives us the ability to customize this for anything. As I said, we can now test quite easily by just using a specific resource that, for instance, logs or tracks all the allocations. This is nice. So we have the ability to inject the dependency to the allocator right here in this set default resource. Does this sound familiar? I hope it does. Yes, one more instance of the strategy design pattern. Different form again, but it's the same idea. We are actually able to customize the behavior to our liking. And this now might be the idea. This might now be the way to actually repair the database example. So it does not work because database is a concrete implementation detail. It is a concrete dependency that we want to get rid of. And so what we now just need in this context to repair it is some kind of abstraction. Some kind of abstraction that inverts the dependencies. And so let's do that. Let's actually deal with this by starting to introduce the abstraction which I now name persistence interface, which is a little more general. Doesn't have to be a database. Can be anything. Could be a file. Could be any system that stores data. So persistence interface, that is a traditional base class. So we have a virtual destructor, cool. We have some read and write function. Note, not virtual, because I'm using another design pattern, the template method design pattern. These functions at this point just called do read and do write, and this is the virtual functions that deriving classes now need to implement. This is the two. And of course, it's slideware, so assume there is, of course, arguments of some sort. So this persistence interface is now the base class for all kinds of persistent systems. We now, in the database.h class, make database derive from this persistence interface. And we make it just implement read and write, which is just a little refactoring to actually get these things, so that functionality in the specific form. Cool, not a lot of work, indeed. Now, we add get persistence interface and set persistence interface. Now, some people have asked, why pointers? Could it be references? Yeah, sure. You could also use references. Perhaps this is even better, but not my primary point of attention right now. So we provide these two functions to actually allow people to change some globally set persistent system, which you might just introduce here as an external variable, which nobody needs to know about. It is the one global thing that, we probably should hide a little bit. But now, in the CPP file, we actually implement this functionality. So first of all, initially, this instance may be null. Nice. And a null pointer. And now, of course, we have set persistence that, if you're given any kind of persistent system, will set the instance to some value. Cool. Quite kind of simple. But get persistence. What do we do here? Well, of course, by default, we could just return the instance. But, well, initially, of course, it's null. So we now have to, by default, set it, for instance, to the database. So if this has not been set, if the database is a null pointer, then, and only in that case, actually create the static database that we've seen in the Meyer singleton. And we just remember a pointer to that database in our instance variable and return this one. Okay, but now, of course, every time we call get persistence, we would check for null. Every single time, which might not be exactly what we have in mind. And also, this might later change some settings. So if somebody explicitly sets this to null as later point, we change it again. So we definitely want to make this initialization once, and exactly once. How do we do this? Well, kind of in the same way, and in a thread-safe way, by just wrapping this in what you call an immediately invoked lambda expression. So we introduce a static bool in it, which is initialized by this little lambda here. And I know it looks scary, but people get used to it, I've heard. So it doesn't have to be any arguments. It's just a little local function that eventually returns true or false. It doesn't matter. You can return any value that you want to, because this is a totally artificial thing. You initialize this thing once and exactly once, but in doing so, you deal with initializing the instance. If it has been set, okay, cool, then we already have one. If it has not been set, then we create a database and remember that one. Now, I've given this talk before, not that this talk, the singleton thing, and immediately people jumped at me and said, it's not thread safe. I know, it's not. At least the initialization is, but set persistence and get persistence are not thread safe. But actually, I seriously don't care. It's a global value. It is a global thing. If you feel like setting the persistence interface, or let's go back to the allocators. If you feel like setting the allocator at some point in the program where other people have already acquired memory and now don't actually know how to give it back, well, then it's your problem. I don't care about thread safety here. There is a certain discipline that you have to use when you deal with global variables. So, no, this should be done upfront at the start of a test, and the start of the main function, wherever. You call this the set persistence interface function once in the program, and then later you have exactly this one thing that you've configured globally. And so, you fixed our architecture. At the top, you have this persistence interface base class. This is now what widget and gadget depend on. They don't know anything about databases. They don't know anything about any specific implementation. They just depend on this abstraction. And a database, although still formally on a high level because it's still part of some database, is totally unknown. Nobody knows about this little thing. And therefore, it really is just a hidden implementation detail. You, however, are now able to just implement any interface, any persistence interface that you want to, for testing purposes, for dealing with this particular problem differently. You can do that on your end and deal with this entire thing correctly. And again, suddenly all the errors go from low level to the top in a high level. This is an architecture. All right. I would now call this an acceptable singleton. Acceptable in quotation marks. This is truly an important point. It's acceptable because we've actually dealt with this dependency inversion. We do not depend on the thing anymore, but on some abstraction. So it's acceptable because we don't no longer depend on the implementation details. And suddenly we can change and we can extend our implementation at will. Whatever we need, whatever we require in a specific context, we can do that. And suddenly also, as I've already pointed out, suddenly we can test this kind of easily. We do not have this hidden thing that nobody knows about anymore. We now have the ability to inject testing code. And so this now enables you to cope with the intrinsically global abstracts. Sometimes. Again, it's a global thing. So I have not given you a free pass to use singletons now. No. The same advice is true. Do not use singletons. But if you have to cope with these few, and they are few, global aspects, then in these few cases, you now have a recipe to actually deal with this in a better way. So, did we now invent something new? Okay, no, not really. I have to admit that this is not my invention. Oh my, no. Actually, there has been this book by Robert Nystrom where this pattern has been described for years. I actually think he has written this in the beginning of the 2000s somewhere. So, this is the service locator design pattern. Provide a global point of access to a service without coupling users to the concrete class that implements it. The patterns are there. The patterns are there. So, as I said before, hopefully I've now hopefully managed to show, design patterns are pretty much everywhere. We just have to see them. We have to realize what is at work. We have to see the advantages that you get from them, but also we should be aware of the disadvantages. And so, as a summary, software design is not an afterthought. It really isn't. It is essential, absolutely essential for the success of a project. I would claim it's indeed the essence that you must not forget. But let's stop pretending that C++ is all about features and standards. There's definitely so much more to talk about. So let's start to talk about the really important aspects of software, which is software design. And in particular, let's talk about design patterns. They are everywhere, absolutely. And so we should learn about the different patterns. I don't know all of them. No, definitely not. And we definitely need to learn about the advantages and disadvantages. Why do we use these different patterns? In which forms do we use these different patterns to achieve the things that we actually want to achieve? And so let's make software easy to change, easy to extend, and easy to test. And so let's start to talk a little about the thing that really matters. Let's talk about to break dependencies. So, thank you very much. So, I know it's late, but are there any questions? If it's a singleton-related question, no, don't use singletons.
No, no, it's not. You mentioned a talk called OOP is dead. I believe the point of that talk is not that much that OOP is dead as a practice, as much as like it's a huge performance problem on modern machines to have bulk processing of heterogeneous objects, because it's just like CPUs are really bad at it.
Yes, that's exactly the point of the talk. The title, however, suggests differently. It's chosen pretty aggressively, But as also said, it's a talk from the gaming industry. And they indeed suffered a lot in the beginning from OOP performance.
Yeah, but I guess then but my question is, how do we adapt all those patterns? Because again, a lot of them are based on virtual and a bunch of like heterogeneous processing, which again is really unperformance. And if you're doing C++, you're here for the performance. If I want virtual, I'll just use Java.
Yeah. But you've seen that strategy is pretty much everywhere. Strategy is, even in its template form, exactly the same idea. So I don't think that it's about virtual functions. This is one way how you can introduce abstractions, one way of many. You have templates too, we have function overloading. I think we just need to explore what options we have to implement these things. And I did do a couple of talks about type erasure, which I believe to be the superior form of dealing with many of these patterns from an implementation point of view. Okay.
Yeah, thanks, Klaus, for the nice talk. Very good topic. But to clarify one thing, maybe I'm wrong, but if you have methods, virtual methods in your interface, and you make them private, you cannot override them in the inheritance, can you?
Oh, absolutely, you can. The private label is an access label. It's not a visibility label. As soon as the driving class actually sees the functions, and they're always visible, you can override them easily. So this is something I also have to demonstrate in my class usually. It's confusing, but the label is not the hindrance. But what you cannot do is you cannot call the functions. So the derived class, the implementations in the derived class cannot call the base implementation because it's private. If you need that, then you make the functions protected, which sometimes happens, for instance, in the decorator design pattern.
And what's the advantage to make it private in the first place? Over making it protected because it's virtual and abstract, so you cannot call it anyways?
I did not explain the template method design pattern, which I personally feel is, again, a huge step in decoupling things. Decoupling the interface of callers from the interface of deriving classes. You have two. You have the public interface and you have the private thing that you override. This, again, gives you a lot of flexibility and changes become so much more easily if something changes later. That's the reason why I do this. No, but not just me, also in the STUD PMR memory resource class, you'll find exactly this pattern for exactly that reason. Changes become simpler. Changes for library implementers.
But you also get that if you make it protected, don't you?
Okay. So I cannot say why this is chosen in STUD memory resource, STUD PMR memory resource, but probably it's not supposed to be called, I guess. Yeah.
I don't have to have a talk about it.
Okay.
Thank you.
So, Victor.
I'm really happy to see yet more talks on software design. I think it's worthwhile our time. My thing with design patterns is that the term implies some kind of universally applicable recipe and codifying existing practice in some recipes that we can uniformly apply in our code. And sometimes there's value in uniformity and recognizing and identifying these architectural constructs. However, they're not always conducive to optimal solutions in concrete situations that we might have. So how do we reconcile the inertia or the tendency to build something that is recognizable or fits within a particular pattern with finding an optimal solution in a very concrete case which might be in conflict with some idealized version of such a pattern?
I know exactly what you mean, but you also said it in the end. It's an idealized solution. It doesn't have to look this way at all. You see that the strategy pattern, which I believe is one of the most common ones, comes in many different forms, but it's always the same idea. I extract some implementation detail because I don't want to depend on this. However, you come up with whatever solution you come up with in order to achieve that. It will be a strategy. So I don't think there is so much a common solution that you should always use. I think it's definitely much more about the intent. What do I want to achieve? How do I want to structure my code? That's what I try to truly point out in the book, that it's always about the dependency structure. What should depend on which in my software? what do I know, what do I not know? And I think this is what we should focus on mostly. Not about this is how we've implemented this in this in the Gang of Four book, but more on what is the dependency structure. I hope this helps.
So focus on the goals of the pattern rather
The
than
intent.
the mechanics of achievement.
Exactly. Yes.
Okay, thanks.
So, Andreas.
Hi, thanks for the talk. I have a question about singleton.
Oh, no. Next question.
So you mentioned that like one of the problems with singleton is that it basically creates a global shared mutable state. If I have data that is immutable, is that safe to put in a singleton always, or do you see problems with that as well?
This is a very, very good question. And I particularly chose a database example. Also, this might not be a great kind of singleton, but because you have to read and write. And then this makes so much more sense, kind of. But as soon as you have something that is constant, as a global constant, or at least uniform in flow direction. So, for instance, a logger only accepts data, but you never read from it. In that case, it might actually work much, much better. If you have something with a uniform direction, this kind of global might work in your favor. But still, the idea that I showed might still help. Yeah? Configuring a logger. So in test, you might not want to write really to file, log the things. No, test, you have other problems. And so this might still help. So, to shorten the answer, this might work if it's truly just unidirectional data flow. It's not as bad. But you have to keep it this way. That's probably the thing that requires extra attention.
Okay,
Yeah.
thank you.
Okay. Another singleton question?
No.
Okay, then you're fine.
Yeah. Thanks for the talk. I have one question. So you mentioned about the mess in the children's room.
Okay.
And he doesn't know how to deal with that mess.
You want to know how it hurts if you stack on a Lego brick, right?
Yeah.
Yeah, okay.
Yeah.
Now,
So since he doesn't have the where to start and how to clear that mess, so are there any strategies or something? Means especially if you are new in some project and there is already a lot of mess,
Yeah.
how we can improve those things? So
there is no general answer. If there would be, I would be out of business. No, but one of the things is usually to identify the pain points, the real pain points, and start there in a localized environment. You cannot change everything right away. This is just too much, too complex, mind-boggling. So start in a local point, things that hurt most. And once this is fixed, actually, you actually see the wood again a little bit. It's clearer. And then you take the next thing and the next thing. It's not easy. I don't say this is easy. It's not obvious what to do, but it's the only thing that does work. Start somewhere and choose the one thing that hurts the most.
thanks.
So Jens, an online question.
How do you know? Yeah, so indeed, an online question. Why can't we use thread synchronization primitives for the global mutable state with the singleton pattern, or why did you not?
You mean here in, so, I cannot ask you. So I assume that this was about the set and the get.
Yes.
If you call set anywhere in a program, if you really feel like this is a good practice, then since it's a global thing, it is indeed like pulling the rug from under somebody's feet. So for all the program, I've used this allocator. Now somebody sets the global thing. I want to give the memory back, but it's a different allocator that might not have any clue how to deal with this piece of memory that I'm not giving back. So if you truly think that setting a global thing from anywhere in the code, and this is where we would have to deal with thread safety, is a good idea, then yes, you have to deal with thread safety. But I would advise against calling set from anywhere, and this is why I don't care about it.
Okay, so your argument is, maybe it's also out of scope for a keynote. but
Yeah.
yes, you could use those, like have a mutex there if you needed that in your application. But
Exactly.
in your case, you say it's better to like do that on the main thread. And
To be honest, in the standard library, these kinds of signals are protected a little better than mine, but I honestly don't see the point. It's global. Okay.
Okay.
Maybe my opinion. Okay, next question.
Just a follow-up to that. If you've got any statically created objects which are making use of like the default...
Could you?
Can you hear me? Sorry.
Yes, thank you.
If you've got any statically created objects which are making use of like that allocator, surely it's never safe to set it.
From anywhere in the program, correct.
Yeah.
Yeah, and this is exactly why I, just as in the standard library, I say set it right up front at the very beginning of a test or at the very beginning of a program in the main function, and I never look back. This is the thing that you will use for
Yeah,
all.
but even if you set it first line of main, if something's already used it, like in a static, a file scope.
That's the usual thing that may happen because singletons should always be available. That's exactly the problem that you have to take care of. So if you truly have dependencies between singletons, then you have, of course, significantly made your problem more difficult to handle.
I mean, it might not even be, it might not even be a singleton. It might be
Some
just
global
any
thing. Yeah.
old
That's
thing that
the
might
usual
hidden
problem
in
of
some source
globals,
file.
correct. So if you want to deal with this, put in the mutex something. But
I'm not so much thinking about that. I'm thinking about the aspect of it. Okay, at startup, the applications use this to allocate something. Yeah. First line of main, someone changes the allocator. Program terminates. Core dumps.
yeah.
Yeah.
You know what's happening right now? You're talking again about implementation details. That's exactly what I usually, what I
I'm
said in the
saying is
beginning.
It's like very, very dangerous to ever use that because you might say, okay, well, it's fine. We just make sure we don't write any code that depends on that, which is we ever make any static objects of. Yeah. 2.5 years later, somebody comes along. You didn't write a big sign on the wall saying never ever use this, never make static foo, because foo's using PMR. Yeah.
Yeah.
Someone comes along
No.
and does it.
I don't say you're wrong. I said you're absolutely correct. It just depends on do you want to deal with this or not. The thread synchronization is not particularly difficult.
Yeah, it's not even about the synchronization. It's about this aspect that you've changed the allocator under the.
Yes.
It's like that's the issue. It's
Yep.
like, this stuff's not going to clean up now.
Yeah, no, I get the point. Yeah, thank you.
Okay.
All right. No more questions? Then thank you very much and have a good trip home.